Hello, Titans. I want to introduce to you the concept of trigonometry and how it applies in physics. Now, I know a lot of you get stressed about trigonometry, so I want to help alleviate that stress by simply saying the only trig that we have to use in algebra-based physics is right angle trig. If you know sine, cosine, and tangent, you're in good shape. If you don't know sine, cosine, and tangent, that's what today's lesson is all about. I'm going to introduce that. And I think even those of you who feel like you know trig, this is going to be a good refresher. So I want to actually build on the motion work that we did in our last unit, and then take it to the next step and apply how that might affect us in terms of our work on studying Newton's laws and free body diagrams and such. So let's start with this example. I've been asked a bunch of times in the last week. Of course, we did vertical launches with kinematics, and then we did straight horizontal launches. But what would happen if you launched at an angle? And don't get stressed, I'm not going to do that right now, but I want to kind of set the stage for how that might be done. So what would we do if we were launching at an angle? Well, what if, for example, someone launched a ball at an angle of 30 degrees, now make it 40 degrees, and at 20 meters per second? Oh, sorry. So what we're used to is horizontal launches, and we know we need to fill in the horizontal template, V, D, and T. And vertical launches, we fill in the vertical template, X naught, X, V naught, V, A, T. But this thing's both being launched vertically and horizontally at the same time. So what do? Well, before you get all stressed, just think about this. It's being launched vertically and horizontally at the same time. So it has a horizontal part of its motion and a vertical part of its motion. So what we're going to do is we're going to take this vector and we're going to turn it into a triangle, which of course is what trig is all about, right? So I'm going to drop this down as a vertical line, and I'm going to look at this as a triangle. Now, I've got one angle labeled. I'm going to shrink it down here. That's my 40 degrees right here. I've got one angle labeled in my triangle. Of course, you could figure out the other three. This is required to be a 90-degree angle if that's horizontal and vertical. And then, of course, you know the other one has to be the complement to my 40. I'm not worried about it right now, but of course, we know what it is. You all know a relationship between the three sides of a right triangle. That's the Pythagorean theorem, a squared plus b squared equals c squared. You also know, as I just mentioned, a relationship between the three angles. They all add up to 180. And of course, if 90 is one of ours, then the other two together add up to 90, just the two of them. But what do we do if we have a side 20 meters per second, and an angle of 40 degrees? How would we find the other sides? Well, that's where trigonometry comes in. So I want to refresh your memory. I assume most of you have seen this word. It's magic word SOHCAHTOA. I would suggest jotting it down in your notes so you can always refresh your memory. Of course, S means opposite over hypotenuse, and S, of course, means sine. C for cosine means adjacent over hypotenuse, and T for tangent means opposite over adjacent. So I'm going to jot down those three equations. Sine of theta equals opposite over hypotenuse. Cosine of theta equals adjacent over hypotenuse. Tangent of theta equals opposite over adjacent. Now, you'll notice a couple things. First of all, I didn't just write tan equals opposite over adjacent. I wrote tangent of theta because tangent is a function. It's something you do to theta. So without the theta, tangent doesn't mean anything. Similarly for sine and cosine. So that's important. Now, I want to come back to this triangle. I know, of course, the hypotenuse, the 20 meters per second. It was launched at that angle. The vector was launched at that angle. But I want to know what's the vertical and what's the horizontal. So let's take them one at a time. What if we want to know the vertical? Vertical is right here. I'm going to call it y for vertical height. Otherwise, I don't want to get confused with my x, the horizontal. So let's see. Y is which side of our triangle? Well, you know the three sides of the triangle. The long side is always a hypotenuse. The other two sides are opposite and adjacent. To me, the opposite is easiest to understand. It's just the one on the far side. So y in this case is the opposite. Adjacent means right next door. So when you're sitting in your class, in your desk in your class, there are people adjacent to you whose desks are adjacent to you. There's one next to you, and one next to you, one in front of you, one behind you. Those are the people whose seats are adjacent to yours. So adjacent means right next door. Well, there's actually two sides adjacent to the 40, the hypotenuse that already has a name, and this one. So this must be the one we're going to call adjacent. So I'm going to call this x side the adjacent. I'm going to call this y side the opposite. Now, that's true from my 40 degrees. But of course, if you were focusing on the 50 up here, the opposite that I labeled opposite would actually now be the adjacent, right? So you've got to recognize that depending on which side of the triangle, or excuse me, depending on which angle of your triangle you're looking at, opposite and hypotenuse could mean different things. So pick one, stay with it. If one is given to you, just use that one. Don't worry about finding the third angle, the complementary angle. All right, so let's do this. I want to know, let's say I want to know y, the opposite side. I want opposite. I already know the hypotenuse, right? So I want to think about the thing I know, the hypotenuse, and the side I want to know, the opposite. That's H and O and H. Which has O and H? That's a sine problem, isn't it? So sine of theta is opposite over hypotenuse. I'm going to start with that. So I'm going to write sine theta equals opposite over hypotenuse. Notice I write the equation I'm starting with. I want to write the, I want to solve in this case for the opposite, right? Opposite is what I want to try and find. So I want to do some algebra to get opposite by itself. To do that, I have to get rid of hypotenuse. So I'm going to multiply by hypotenuse. Now I can say opposite equals hypotenuse times the sine of theta. Instead of writing OPP, I just write O. Instead of writing HYP, I just write H. That's pretty typical. But I want you to look at that. Compared to my triangle that I wrote up in the top left, the opposite is the y side, right? The hypotenuse is the 20 meters per second, the vector, the original vector. So here's kind of a shortcut, and this is a shortcut that physicists use all the time. I'm going to simplify this. Instead of saying opposite, I'm going to say y. Instead of saying hypotenuse, I'm going to call it v for the vector. So I've written myself a generic equation right here. Y is v sine theta. I can do the same thing for the x. The x is the adjacent side. I know adjacent, and I want adjacent, and I know the hypotenuse. That looks like a cosine problem, right? So let's see, I can say cosine of theta is adjacent over hypotenuse. And since I'm trying to find adjacent, I can multiply by hypotenuse. And I can say A equals H cosine theta, or to use our shortcuts, could I say the adjacent, that was the x, is equal to the vector times the cosine of the angle? So whenever you know the vector, the angle that something is launched at, if you want to find the x side, you can just take that vector times the cosine of the angle. If you ever want to know the y side, you can say v sine theta, the vector times the sine of the angle. Now, if we were doing trigonometry, if we were doing kinematics with this, all we would do is find our x and our y right here. We plug our y in as the initial vertical velocity. We plug our x in, our x velocity, because the velocity is 20 meters per second. We use our x as our horizontal velocity. And then we go ahead and do do kinematics, just like we always have before. So two-dimensional kinematics when we're launching at an angle isn't all that hard. It's just that you have to do this extra little step of figuring out what the initial velocity was, how much of it's going up, how much of it's going sideways. Okay, now, I do that to introduce our next section, which is, of course, we're studying forces, right? But the same thing could be true if this was 20 newtons at an angle of 40 degrees. I could find how much of that 20 newtons is pulling us up, how much is pulling us sideways. This is exactly what I would do here. In fact, let's do that. Let's suppose I'm going to change my 20 meters per second, 20 newtons. Okay. And now what I'm going to do is I'm going to find my y. Say v sine theta, my shortened equation. My vector is 20 newtons. That's a force vector. And the sine of, what did I say, 40 degrees? 40 degrees. Do that and I can calculate my vertical force. I can do the same thing for the x. I can write v cosine theta. That's my x equation. My vector is 20 newtons times the cosine for it. And it's as simple as that. Now I'm going to grab a calculator. So you want to be aware of a couple things in your calculator. First of all, on your calculator, make sure that your mode, and it's never mattered before, but make sure your mode is in degrees mode. Mine was not. So make sure your mode is in degrees. My calculator has a DRG button, degrees, radians, gradians. I want to make sure it's set for degrees because this angle was 40 degrees. Very rarely do I give you an angle in radians. Never will I give you one in gradians. Those of you who are in pre-calc trig where you start dealing with radians, you might have to make sure you go back and forth with your calculator, but make sure you're in degrees mode. So what do I have? 40 degrees. So I'm going to do, my calculator makes me do sine of 40. That's 0.64278 times 20 newtons. That gives me 12 point, I'll call it 12.9. And because that was in newtons, this is in newtons. And now if I want the x component, I'm going to do 20 times the cosine of 40. And I get 15.3 newtons. So some of you might be looking at this saying, okay, this is weird because 12.9 and 15.3 do not add up to 20. So how am I saying this 20 newtons has a horizontal component of 15.3 and a vertical component of 12.9? Well, because when we add a horizontal and a vertical to get the hypotenuse, we have to do the Pythagorean theorem. And I'll bet you, if you pause this video and check it out, 15.3 squared plus 12.9 squared should be equal to 20 squared, because that has to work. It's math. All right. So why would I do that? Okay. So that's an important thing, is to be able to do that. But now I want to talk about applications. Anytime you know a force in a certain angle, we don't like angles. We like straight up and down. We like straight sideways. We do not like anything with angles. So whenever you see it, always start by saying, okay, I know I've got something at an angle. I'm going to do this trig piece. I'm going to break it into components. By the way, if this vector was 20 meters per second in the third quadrant at an angle of, let's call it 200 degrees. I know the triangle looks a little funky. You could draw one down like that. But if you just do x equals v cosine theta and you plug in 200 degrees as your theta, it's going to get the right number, and it will also correct your sign. It'll give you a negative sign because in this case the x is pointing left or negative. When you do that with the y, when you plug in v sine theta, if theta was 200 degrees, you get a negative y, meaning the y component is pointing down. So this vector is pointing left and down. So trig is kind of a nice thing once you figure out your basic equations. Okay. Now I want to do a different kind of concept. I want to put this together with a realistic problem. So I'm going to erase this mess. We should have left SOHCAHTOA at the top of the board because it's kind of a nice thing to look at. I'm going to jot that down again. All right. So how do we apply this in our current material? Well, what if I draw a free body diagram of a sign hanging from a building? Maybe it has, well, I always ask when I draw free body diagrams, what forces are acting on the sign? Well, there's always gravity pulling down, mg. Let's suppose this sign is hanging from a rope that's pulling up here. Ropes have a force, but I'm going to call it a T for tension. I'm going to call that tension 1. And let's suppose, for the sake of argument, that there's also a horizontal rope over here. I'll call that tension 2. Now, tension 1, maybe I measured, is at 30 degrees. It's at 30 degrees right there. What if I tell you that the mass is 20 kilograms? Okay. And I want to know what's the tension in these ropes. So when you first look at that, you think, okay, that's too hard. No, it's not. It's physics. It's not a big deal. So what we're going to do is we're going to first use this trig piece that we just looked at. We're going to say, all right, this one's straight down. I don't mind straight down. This one's straight sideways. I don't mind that either. This one, however, is kind of messy. So what I'm going to do is I'm going to break this into components. Make a triangle out of this thing. Now, if you were actually taking an AP test, you wouldn't want to draw the triangle right on the original three-body diagram, because on an AP test, they get really uptight about that. They want you to draw just the original vectors on your drawing, not components of them. So you would draw a separate diagram over the side, but for this, I'm not going to worry about it. Okay, so for T1, I want to know how much of it's pointing in the Y and how much is in the X. Okay, just like before, we already know the equations. For the Y, I can say, well, the Y component is going to be V sine theta. Vector is T1 times sine of theta. Now that's annoying because I didn't give you T1. That's okay. How about X? Well, X, we just said, is going to be T1 cosine theta. Okay, that's not quite as nice as what I just showed you. Before I gave you the theta and I gave you the angle, presume I gave you the vector, the tension, and you can just plug in your numbers, but I can't do this here. So what do? Well, I'm going to rely on Newton's first and second laws. Newton's first law says this object, the sign, which is presumably hanging at rest, has to have balanced forces on it. So if it has balanced forces, that means the up and down forces better balance each other, or this sign would be rising up into the air, accelerating upwards. Or if the down force is bigger, it would be accelerating downwards. And neither of those is true, of course. The sign is hopefully not accelerating right or left either. So that gives me the ability to write some equations based on this. I can say that up equals down for this problem. What's pulling up on this sign? Well, the only uppish force is this V sine theta. So I can write V sine theta equals the down force, the only down force is mg. And I've written myself an equation, and since I know m and g, and I know theta, I'll bet I could find v. In fact, I'm going to do that. Now I'm going to show you one other difference from what we've done before. In the past, we always filled in what as g? Negative 9.8, right? Well, do you see my arrow pointing down? That down arrow is telling me the negative already. So the fact that I'm using that negative sign in my arrow means I'm just going to fill in negative 9.8. Hello, sir. So there's my, whoops, sorry, I'm not using my negative sign because that's part of my arrow. So now I can do 20 times 9.8, which is 196 if I'm not mistaken. And we found out last time kilogram meters per second squared is a Newton. That's 196 newtons. So I just found the vector, or in this case, T1, 196 newtons. Cool. How about side to side? I know it's balanced, so I know left equals right. So what's pulling left? Well, that's T cosine theta. What's pulling right? Well, that's T2. Actually, I should have written T1 cosine theta, shouldn't I? And over here, for some reason, I changed my V, my T1 to a V, but I put it back at the end. So V for the vector and T1 for tension 1, they mean the same thing in this case. This vector sideways to the right is T2, up at an angle is T, I'm going to call that T1. But I know T1, so I can find T2 with no problem at all. It's going to be T1, that's 196 newtons, times a cosine of, oh my gosh, I'm an idiot. I forgot my trig. I forgot to divide by sine of 40, sine of 30. Sorry about that. So my answer wasn't 196. My answer is 196 newtons divided by the sine of 30. Sine of 30, as it turns out, is 0.5. So 196 over 0.5 is 392. If I mathed that right, I think I did. Sorry about that. Now I can come back here, and I've got 392 newtons times a cosine of 30. That one I can't do in my head. I know the cosine of 30, but I can't multiply it by 392. 392 times cosine of 30 It's 3:39. Now I know tension 1 and tension 2. Relying on a little bit of trig to break angle vectors into straight up and down or straight side to side. And then I can simply write some equations. Up equals down, just like we saw in our last video. Left equals right, just like we saw in our last video. Combine those and we can do magical things. So hopefully that helps. Sorry about my screw up over here with my trig. I lost my sine 30. But I hope this makes sense, especially when we couple it with our last video, which was how to set up free body diagrams in the first place. Awesome. I hope you guys get this figured out. We'll certainly be dealing with it in class. Have a great day, everyone.